Alright guys, so we're going to really focus on the quantitative aspects of thermochemistry. So looking at how you can tell how much heat has been exchanged with a system, how much heat an object has gained or how much heat an object has lost, or how much energy overall it's going to take to make changes in physical states, or just changes in energy. So if you remember, we've already talked a little bit about specific heat capacity. This is referring to how much of a substance you have and what the substance is made of. Different objects have different specific heats. So some are going to heat up a lot faster than others. So here in the diagram, I have 1 kilogram of gold versus 1 kilogram of water. If you notice there's a change of 70 degrees, so if we add the same amount of heat to both, the gold is going to heat up a lot faster than the water will. The water is not going to have as much change in temperature when adding the same amount of heat. Remember, this refers directly back to their specific heats. So the specific heat of gold is that 0.129 joules per grams times degrees Celsius, whereas the specific heat of water is 4.18 joules per gram times degrees Celsius. So the gold specific heat is a lot lower, so it is going to heat up at a much faster rate than the water will. So our main equation that we're going to use for a lot of our thermochemical equations is this Q equals MC delta T, where Q is referring to the change in heat. Usually it's going to be measured in joules. Sometimes you may see it in calories. The M is going to be our mass in grams. The C is our specific heat, which is in that joules per grams times degrees Celsius. And our delta T is going to be our change in temperature, and we're going to have that in degrees Celsius. We don't have to change for Kelvin for these. And remember, if you're given two different temperatures, that change in temperature is always the TF minus the TI. So you always want the final temperature minus the initial temperature, because this will determine if that change in temperature is positive or if it's negative. But you always want to do the final minus the initial. Another unit you'll see for heat, for Q, is calories. So make sure to look up, go through the other videos, and you're going to have to be able to convert between joules and calories. It'll be a simple one-step stoichiometry problem, just to do that quick little unit conversion. But don't freak out if it shows you calories instead of joules. So here's a sample problem. It says the temperature of a 95.4 gram piece of copper increases from 25 degrees Celsius to 48 degrees Celsius when the metal is going to absorb 849 joules of heat. And it wants to know what the specific heat of copper is. So remember, we're using our same equation. Use our same equation, that Q equals MC delta T. See what variables it gives you. So pay attention to those units. So if you notice, Q is our heat in joules. It did give us joules. It gave us 849 joules. Mass is in grams. It gave us 95.4 grams. Specific heat is that joules divided by grams times degrees Celsius. It's asking for specific heat, so we currently do not know our C value. And then for our delta T, our change in temp, it says that the temperature increases from 25 degrees Celsius to 48 degrees Celsius. So remember, our final temperature is that 48 minus our initial temperature, that is the 25. From here, you can go ahead and subtract those before calculating. Do kind of keep in mind, be consistent with your sig figs. So if you subtract these, you get 23.0 because they both have one digit currently. So then whenever you multiply these together, or you do the 849, divide by the 95.4, divide by the 23, you get that your C value is going to be 0.3869 joules divided by grams times degrees Celsius. But always keep in the back of your mind sig figs. So if you look, the 849 currently has 3 sig figs. The 995.4 has 3 sig figs. When you did your change in temperature, the 48 minus the 25, they both had 1 decimal place, so we have 23.0, which has 3 sig figs. So our answer needs to be rounded to 3 sig figs. So you want to round it to that 3rd decimal place. So our specific heat is going to be 0.387 joules divided by grams times degrees Celsius. So always remember in the back of your mind, think about your units and think about your sig figs. Let's look at another one. Here, wants to know how much heat is required to raise the temperature of 250.0 grams of water by 52 degrees Celsius. One thing that you are going to have to know is the specific heat of liquid water. If you have not memorized that already, that is something that you want to memorize. It is not given to you on your reference sheet, but we are going to use it a lot. Any other specific heats that you need will be given, but water you are expected to know. So we're going to use the same equation. Our Q equals MC delta T. Here it's wanting to know how much heat is required. So it's wanting to know our Q. We do not know that value. It gives us a mass of 250 grams. Our C, our specific heat for liquid water, is 4.18 joules divided by grams times degrees Celsius. And then our change in temperature, it told us that the temperature raised 52 degrees Celsius. So it has already subtracted that for us. So we do not have to do our final minus our initial. So if you type this in the calculator, do the 250 times 4.18 times 52, you get that our heat is equal to 54,340 joules. So go back and look at your sig figs. The 250 has 4 sig figs. The 4.18 has 3 sig figs. But our 52 degrees only has 2 sig figs. So our answer can only have 2 sig figs. So we can say our energy is actually 54,000 joules. You can also write that in scientific notation, but remember changing it to scientific notation, it's that 5.4, and that is 2 sig figs. You do not have any extra zeros on here. Times 10, and we move the decimal 4 times. If you put it in scientific notation, make sure to remember your unit, but double check your coefficient and make sure that you have the correct number of sig figs. From Chem 1, if you remember, another part of thermo we talked about is what happens when it changes phases. So these problems we've done so far have heated up, but it's still been the same phase of matter. It has not changed. Whereas a lot of things, specifically water, if you heat it up enough, it goes from a solid into a liquid. The liquid, if you heat it up enough, it's going to change into a gas. So you have to account for those phase changes in there. So that's where we had a heating curve. It's a graph of the temperature versus time for processes where energy is added at a constant rate. So you'll have temperature on the side, time going across the bottom, and we're adding heat at a constant rate, not bit by bit. It's going to show the physical changes that occur as heat is added. So the actual changes in temperature, how the temperature is going up, and it will also show you where there are changes in state. We're pretty much going to look at the heating curve for water. That's one that you need to be familiar with, know the values that go with it. But there is a heating curve for every substance, but maybe the melting point and boiling point are at different temperatures, or it takes a different amount of energy for some of those changes. So hopefully this looks familiar. This is our heating curve for water. So some things to look at. Remember, we have temperature on our y-axis, time on our x-axis. And if you notice, this is not a linear graph. It is segmented. So each segment represents a different change that's occurring. So since this is water, we start off at the colder temperatures and we have solid water, so ice. It then goes through from B to C, where it is changing. So if you notice the temperature does not change, that's a phase change. That's where it is actually melting. So the temperature at which that melting is occurring is 0 degrees Celsius. So that first flat line is at 0 degrees Celsius. Then the segment from C to D. The temperature is increasing, it's going up, and it's above 0 degrees Celsius, so that's where we have liquid water. Then once it gets to D, you have another flat line. So remember, the flat lines are phase changes where the temperature is not changing, but the heat energy is. So where that flat line is, and it's changing from a liquid into a gas, which is our next step, is going to be that 100 degrees Celsius is where it's going to stop being a liquid and that phase change occurs. And then where it's E to F, it's already it's above that 100 degrees Celsius, it's boiled. So that is going to be gas or steam up at the top. So kind of note where those phases are. If you remember back from Chem 1, where those phases are. So between A and B where it's ice, between C and D where it's liquid, and between E and F where it's a gas, those temperatures are changing. So that's where we use our Q equals NC delta T. So that equation is used specifically when that temperature is changing. But you need to make note of when the temperature is not changing. So between B and C and D and E, those are phase changes. So the temperature is not changing, so you need to use a different equation. So remember, when the temperature is not changing, that's when we use our Q equals, and in Chem 1, you had values on your reference sheet for joules and grams. With AP, you're going to be given values in kilojoules per mole. So our equation looks a little different. So our equation is not going to have temperature in it, but it's going to be Q equals N stands for moles, times delta H, which is going to be the change in heat. So I said N is moles, and that's going to be our heat constant or change in heat. So down between B and C, this part may look familiar from Chem 1. That is our delta H of fusion. So talking about how much heat is required to melt that solid ice into liquid water. It takes a certain amount of energy. From D to E, where it is boiling, that is our heat of vaporization. Because it's vaporizing, changing from liquid water into steam. So I told you you have to know the specific heat of liquid water. That was that 4.18 joules times grams degrees Celsius. If it is something with ice or gas, you will be given those values, but remember they have a different specific heat than liquid water. So ice is going to have a specific heat of 2.10, and that's going to be the joules divided by grams degrees Celsius. Whereas steam is going to be 1.99 joules grams degrees Celsius. So those will be given to you in some of these multi-step problems. The only one that will not be given is that 4.18. You have to know that. Values for delta H will also be given when appropriate. So you're going to see the heat of fusion is going to be 6.02 kilojoules per mole. So yet again, that's a little different from your values from Chem 1 because all of those were in joules and grams. And your delta H of vaporization is going to be 40.7 kilojoules per mole. So we're going to use those values with some of our calculations. You may need to know those as you're going through sample problems, but on a quiz or a test, those values will be provided to you, except for that specific heat of liquid water, that 4.18. So let's look at how to do a problem like this. If you remember back from Chem 1, we did several of these. We talked about figuring out where on that heating or cooling curve you're starting at and where on that heating and cooling curve you're ending at. So I'm going to write our two equations up here. So remember we had our Q equals MC delta T. And then we had our Q equals N delta H. And if you look at a rough sketch of a heating and cooling curve, that will help you out a little bit. So this problem wants to know how much heat is required to convert 50 grams of liquid water at 22 degrees Celsius into steam at 105 degrees Celsius. So if you pay attention, remember on this graph, the first flat line is 0, the second flat line is 100. So if we're starting out as liquid water at 22 degrees Celsius, that's right about here. And then we're changing into steam at 105 degrees Celsius. That's above the 100, so in our gas phase, so right there. So you kind of have to look at what phases you're going through and what changes are occurring. So I kind of like to write this out to the side for myself because I know if I'm starting at this 22, I'm heating up that liquid. So I'm going to have a liquid step. So while it's a liquid, the temperature is changing. So remember we used that first equation, that Q equals MC delta T. So if you pay attention to that, our mass, it told us was 55 grams. Our C, since we are liquid water, our C is that 4.18 joules divided by grams times degrees Celsius. And here's where people tend to mess up is that temperature change. So remember, temperature change is final minus initial. You have to pay attention to the final temperature that that liquid water can reach is 100. Once it goes above 100, it changes phase. So from there, subtract our initial temperature, that 22, and that's our first step. So if you punch that in the calculator, you get 17,932.2 joules. So I'm going to leave that and we'll come back to that in a minute. So then if you look back at your graph, once you've heated up that liquid water to 100, you now have to go across that flat line and change into a gas. So remember, the temperature is not changing when you're going from a liquid into a gas. So we have to use our second equation, our Q equals N delta H. So this is where it's a little bit different from what we did in Chem 1, because Chem 1 you had everything in grams. But if you remember, our values for delta H are in kilojoules per mole. So we cannot do grams times kilojoules per mole. We have to plug in moles for N. You can do that in one simple step. So remember, we have 55 grams. So if you multiply that by our conversion factor to change to moles, so remember 1 mole of water is 18.016 grams. So if you do that one step, it's changed to moles for you. So you don't have to change to moles in one step and then plug it in. You can do it all in the same equation. So that is our N, and then that gets multiplied by our delta H. So remember, up here, between liquid and gas, that's our heat of vaporization. So you want to make sure to use the right value whenever you're calculating this. So remember, the heat of vaporization was that 40.7 kilojoules per mole. So whenever you punch that in the calculator, it gives you 124.251 kilojoules. Now, if you notice, we have kilojoules in one step and joules in another, so we're going to come back to that. We want to finish out and make sure that we do all of our changes. So first we heated up the liquid water to 100, then we changed it into a gas, but still at 100, so we're at this corner right here, but we have to heat up to that 105. So we have one last gas step. So while it's a gas, the temperature is changing. So we go back to that first equation, that Q equals mc delta T. So remember, our mass is still 55. Our C, our specific heat for steam, would be given to you on a quiz or a test, so that was the 1.99 joules divided by grams times degrees Celsius. And then our change in temperature. Our final temperature of that liquid, or of the steam, is going to be 105 degrees. And the steam started at that 100 degrees, where we left off from heating up the liquid. So if you calculate that going across, you get 547.25 joules. So now we have to do a couple of things to make these equal, because remember, our last step was to add them together, but we cannot add the joules and the kilojoules and get a valid answer. So we want to change them to be in the same unit. I like to change them into kilojoules. It makes it a little bit easier with your sig figs. Simply because if you change everything to joules, you might end up with hundreds of thousands. So I'm going to change everything into kilojoules first. So remember, that moves the decimal 3 times to the left. And while we change to kilojoules, I'm kind of going to pay attention to sig figs. So our first equation with the liquid, if you pay attention, the 55 has 3 sig figs. The 418 has 3 sig figs. And then with the subtraction, the 100 minus 22, that is going to be 78. And remember, subtraction, it's whichever decimal there is, so that has no decimal points. So this has 2 sig figs. So you want to move your decimal 3 times to the left to change to kilojoules. So we're going to put our decimal right here in our new number. But we want our answer to only have 2 sig figs. So we're going to make this 18 kilojoules. Our second one, the 124.251, even though it's already in kilojoules, we need to think about sig figs. Make it a little bit easier on ourselves. So our 55 grams had 3 sig figs. Don't bother conversion factors when looking at sig figs, so you can kind of ignore the 18.016. So 55 had 3 sig figs, and our 40.7 had 3 sig figs. So we want to round this answer to where it has 3 sig figs. So we're going to change this to 124 kilojoules. Whereas on the last problem with a gas, this one gets a little funky. So we know we're going to change to kilojoules, so we're going to have to move 3 decimal places to the left from our original number. But the 55 has 3 sig figs. The 1.99 has 3 sig figs. If you subtract 105 and 100, that is 5 with no decimal places, which is only 1 sig fig. So when we round, we want to round to 1 sig fig. So this is going to be 0.5 kilojoules. Now that everything is in kilojoules, we can add them together. And then pay attention adding. Whenever you're adding, the 18 and the 124 do not have decimal places. So we want to round to where we have no decimal places. So if you add those all together, you should get 143 kilojoules as your final answer with sig figs and everything. So it's a lot of steps to this process, but make sure to always keep in the back of your mind at the end, go back, make sure they're in the same unit before you add them together, and then make sure that you pay attention to those sig figs. There's some more practice problems like this throughout the unit checklist and stuff like that. We'll go over some more in class. One thing to note is if you see one that looks like this, remember this one is a cooling curve for water, so it's kind of flipped from the heating curve. You're using the same numbers, but it's all negative temperature changes or negative energy. Energy is being taken away. So one thing to note, if you're doing these calculations, they work in the same way. Your 3 lines, if you notice, they are all going to have negative temperature changes because it's going down. So whenever you calculate for Q, for all 3, you are going to end up with a negative Q because it is losing heat and losing energy. Where we had our heat of vaporization, which is normally here, this is negative because we're losing heat. Therefore, it is our heat of condensation. So it's going to be the same value, but negative. So this will actually be that negative 40.7 kilojoules per mole. Whereas it's freezing. So here we used to have our heat of fusion, but now it's negative. It's going down. So it is actually our heat of solidification. It's yet again the same value, but negative. So this is actually going to be that negative 6.02 kilojoules per mole. So one thing to note, if you are doing calculations like this and the temperature is going down, all values will be negative. A lot of people mess up on this, and their actual phase values with the Q equals MC delta T will be negative, but they forget to make that delta H negative, so they end up with 1 negative value and 1 positive value. That's incorrect. All of your Q values are either going to be all positive if it's endothermic, or all negative if it's exothermic. So those are some things to pay attention to as you're going through these problems. I know this is not easy. You have to pay attention to all of your steps. The easiest thing is to forget those phase changes. So be careful as you're going through sample problems while working through the homework. Come to class and ask me things if you need to.